And let's give a hand to Jenny.
Okay. Let's see if I can attach these. There we go.
That'll work.
Yay. All right. So one of my research topics is studying actually planetary defense. I work with asteroids and impacts on asteroids, and so that's why I was glad Dr. B asked me to give this presentation, because it's one of my favorite topics.
And this is going to be on exam 3, so make sure you take notes. We're recording for YouTube. Take notes, my friends.
All right, so today I'm covering just a little bit on comets, asteroids, and then what do we do if they're coming towards us. Comets, the way that I learned what a comet is that it's basically a dirty snowball. They're basically just chunks of ice and dust. There's not much to it, except they're like one of the most complex bodies in our solar system. So they orbit the sun on very eccentric orbits. So we know that the planets orbit on eccentric orbits, but in comparison, these bodies come flying in from way outside of the solar system, do a tiny pin curve around the sun, and go flying straight back out. Most of these comets come from the outside of the solar system from somewhere called the Oort cloud. This is just a massive cloud of dust, gas, basically leftovers from the early solar system surrounding our solar system. So the comet structure, when you look up in the sky, this is what you'll see. Do I have a cursor? Oh, yeah. There you go. You'll see basically this like blurry streak. Oh, there we go. And there'll be 2 tails on it. One is going to be a dust tail, there, and the other is an ion and gas tail. And basically what happens is the sun is going to sort of melt the ice and gas within the actual nucleus, which is the main core part of the comet, and the gas and dust will go flying off. So the comet has this little snowball chunk at the head of it, and this is called the nucleus. So this is actually really hard to see because it's surrounded by something called the coma, which is this bright cloud of all the dust and gas and ions that are coming off of this. So one of the reasons that you see 2 tails, it's hard to see here, this little light streak in the background here is the gas and ion tail.
It'll look better in YouTube.
Yeah. And then this big tail is the dust tail. The reason there are 2 is because the solar wind actually pushes the ions from the comet into a separate tail in separate direction coming off of that.
What is the solar wind?
It's like the solar wind is a bunch of particles essentially that are coming off of the sun. So these particles interact with the gas particles flying off of the comet and get pushed away. So there is a famous comet. This is going to be a clicker question here. There's a famous comet called Comet Halley. You've probably heard of it. And it can be seen in the night sky about every 75 years. So this here is a picture of Comet Halley. You can see its ion tail and dust tail. Last time we saw this comet was in 1986. So that was before most of us were born. Before I was born, anyway. So the question is, in what year will we see Comet Halley again? So this is a numeric one, so you're going to be putting in a number.
Hit the refresh key.
Yes.
And then type in your number, and then what?
Hit send. Don't forget to hit send. Hint, you will see it in your lifetime. Hopefully. That's what you hope for. Do some quick calculations. All right, I'm going to give a couple more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So, we're going to see Comet Halley next in 2061. So make sure to have a telescope ready and keep an eye out for that. You can even put it in your calendar now, and then you'll...
Only 43 years.
Yeah, 43 years in advance. You'll look down at your phone and be like, what
And
is
if I'm still around, I'll say, why, Sonny, when I was your age?
So kind of transitioning to asteroids, because asteroids have a bit more to do with planetary defense since we encounter them a lot more often. An asteroid is basically a large rock. Like the comet was an icy rock, this is just basically a large rock. And the difference between an asteroid and, say, a moon is that the asteroid is just orbiting the sun, whereas a moon orbits another body, like a planet. And some of these asteroids can actually be larger than moons. Well, some moons. Moon of Pluto, it's larger than often. So they range in sizes from being like meter sizes up to hundreds of kilometers large. So there's a wide range in boulders that they can be. They're actually, the larger asteroids tend to be more spherical and look more like moons, and often they have different layers in them, like the Earth has an outside crust, a molten mantle, and an iron core. They'll have a similar structure, and so basically long ago they were heated up, and these rocks, as they were forming, separated out into a small iron core, a molten mantle, which then usually cools because it doesn't have tidal forces on it, keeping it warm. And then like a crust on the outside. So each of these layers will have a different composition. Now, it's not usually true for the smaller asteroids. A lot of the smaller asteroids we see are either fragments of the bigger asteroids from explosions and impacts, or they were never heated at the same rate as the larger ones, and so they're just kind of a agglomeration of all the different compositions all in one. So there are several places where we find asteroids in our solar system. The most common is the main asteroid belt, and this is between between Mars, which is this little red line right here, and Jupiter, which is this kind of yellowy orange line here. And even though it expands this massive area in our solar system, if you added up all of the mass in this area, it's only going to be about 4% the mass of our moon. So it's still fairly spread out, but it's just a bunch of little rocks. You wouldn't want to fly your spaceship through it. we have another population of asteroids called the Trojan Asteroids, which is interesting for me because later on I'm going to be working on part of one of the missions to travel to the Trojan Asteroids to study them. These asteroids travel in front and behind of Jupiter, so this here is Jupiter's orbit along this line. The arrow is pointing in this direction, so Jupiter follows this path. Here's the sun, and there's a little cluster behind Jupiter and in front of Jupiter. And these asteroids were from the main belt, and they fell into these like stability points in front and behind of Jupiter. And it's interesting because they're exactly 60 degrees away from Jupiter. And then we have a mission that I talked about just a few seconds ago called the Lucy mission, which was just approved to go out and study a bunch of these asteroids. And they're going to basically do a bunch of flybys of these asteroids. So switch over. So this here is an animation I like because it shows the red dots here are the main belt asteroids, and the green ones are the Trojans. All the little whirring dots in the center are the terrestrial planets, and then the big orbit on the outside is Jupiter's orbit. So you can see how the main belt forms kind of this triangle where there are these stability points in Jupiter's orbit. And then the Trojan asteroids just kind of always stay in front and behind of Jupiter on this path, and kind of switches off with some of the main belt asteroids. And switch back. We also have another group of asteroids which are the most hazardous for us because they are the near-Earth objects, or NEOs. And these are basically comets and asteroids that have fallen into orbits that are around the region of Earth's orbit. Occasionally we'll get a comet that orbits around us. Mostly it's asteroids because the comets are too warm and so the ice melts and all the comet dissipates. But actually if you go out in August and see there's a meteor shower called the Perseids, and that is actually when the Earth's orbit crosses through kind of the debris left over from a comet that basically melted along our orbit. And so we go through this dust, and as we go through this dust that's left over, it will burn up in the atmosphere and basically create these little streaks across the sky. So you're not actually seeing shooting stars, you're seeing basically burning up and shooting bits of rock and dust, which is pretty neat. So the composition of the near-Earth asteroids hasn't changed a whole lot since the formation of these asteroids and the solar system about 4.6 billion years ago. Because these are the ones that just kind of came out into this area and sat around. They're fairly spread out in comparison to the main belt, and so they don't collide a whole lot. There isn't a whole lot of interaction between these asteroids, which is good for us because it means we have a fairly clear orbit and don't come across them very often. But since they are the closest to Earth, they have the highest probability of impacting Earth. So before I go on, does anyone have any questions on asteroids, comets, anything? Yes?
Since the comet is mainly ice and dust, are they getting smaller, or do they stay about the same size as they go around and collect more ice and dust, or do they just get smaller and then eventually disappear?
So the question was, do the comets get smaller over time, or do they kind of accumulate more dust as they go? And the answer to that is they typically get smaller over time. The longer they spend out away from the solar system, they'll have a longer time to collect more dust. But typically, comets just kind of constantly are spitting out gas and dust. They'll spit it out slower, farther away from the solar system, and a lot faster closer to the solar system or closer to the sun. But they'll just kind of constantly, slowly spit out material. So they are always shrinking. They typically don't collect a lot of material, except if they're out in the Oort cloud where there's a lot of dust that they can collect. Yeah?
So basically, like, I guess in like far future there would be no comets.
So yeah, in the far future, it's possible that we will have no comets. Chances are, like out in the Oort cloud, we don't know a whole lot about the Oort cloud because it's so far away. Chances are there are still maybe a couple comets that are forming, but most of the comets that we see are going to eventually dissipate. So long, long in the future.
So like the comet is like something from the like that area and basically falls in towards the sun.
So the question is a comet basically something that starts out in the outer solar system and then does it fall in? They have actual orbits, so they are sort of like, they have orbits similar to like the planet's orbits, except instead of being almost circular, they're very eccentric, very kind of ovular. And so it'll come flying in from very far away and make a very small turn around the sun and come flying back. So it's almost a straight line in and out. But there is some sort of orbit that they follow. They don't just fall in. Unless it melts when it falls in, then it just falls in and melts. Anyone else? Yep.
I saw in one of the diagram, the asteroid belt seems to be getting smaller than the planets. Is that how it works, or was that just conceived in the diagram?
This one. Yeah, so the question was, in this little video of the Asteroid Belt and Trojans, do the asteroids in the main belt orbit slower than the planets? And the answer is yes. They do have a slower orbit. They're farther out, and objects that are farther out tend to have slower orbits. They tend to have just like a leisurely stroll around the sun. There's not a whole lot of mass there either. Yeah, so planets just fly around in comparison to these asteroids, which actually makes it a lot easier for us to target them for research missions and such, because they, in comparison to the Earth, they're just sitting in one place. Switch back. Yep.
If that's the case, then if we're going fast, we don't like only have to like we would have to time it because we're moving way faster.
Yeah, we do have to time how, like when we leave, since we're going so much faster, but it's easier to be moving quickly on our own body than to have to try and hunt down something that's also moving quickly in a different direction. So, anyone else? Okay, so I'm going to talk next a little bit about some of the risk and how we deal with the risk of asteroids. So the Earth, whether you know it or not, is actually constantly being impacted by debris. So whether this is just tiny little pebbles, most of the time it's really small rocks and dust that we can't even see. And a lot of times it just burns up in the atmosphere and makes a pretty little streak across the sky, and everyone makes a wish because it's magical. But sometimes bigger objects can hit us. And when the bigger objects hit us, it can either be catastrophic or catastrophic for 1 or 2 people. And by that I mean sometimes a big rock will hit us and most of it will burn up, but then there will still be this little pebble that comes flying through the atmosphere and impacts down on Earth. And I actually had a friend in undergrad who had his car hit by a meteorite. It was just a really small chunk of rock, and it left this little dent on the front of his car. He was lucky it was the car and not him, because those injuries are pretty gruesome. But if you go outside and look around, you can potentially find some of these rocks that have fallen through the atmosphere. And there are a couple different types to look for. So there's one that looks just like a rock, and those are the stony meteorites. And so those are gonna it'll look like every other rock. So those are hard to find down here. They're easy to find up in Antarctica because there aren't many rocks. And up at the North Pole where it's just ice, and you can say, oh, there's not supposed to be a rock here, but there is a rock, so it must have fallen from space. And then the other type that's a lot easier to find, and if you watch out on the ground, you might find one, and those are the iron meteorites. And those are basically just solid chunks of iron. And they look very dark. They basically look like black rocks, which in comparison to the sand and limestone that we have here is pretty easy to spot, thankfully. So if you're ever out on a hike and not being chased down by gators, and you find a little black rock, you might want to pick it up because it could be a meteorite. If you're in other countries, you have to be careful with the laws of picking up rocks off the ground, but if in America, if you find it, it's basically yours, which is great. Makes our lives easier. So what is the big risk? Basically, space isn't as empty as we all made it out to be. It turns out there's still a lot of debris that's floating around, and we're still even launching a bunch of space junk up, satellites and such, and those can even fall back down and impact on Earth. And if they don't burn up in the atmosphere, they can still pose a hazard for us if someone's glove falls from space and hits them on the head, which did actually happen once. There was a glove left out in space just floating around, and it fell back down, didn't burn up in the atmosphere, and hit someone on the head. So watch out. Don't just watch out for gators, you gotta look up and watch out for stuff falling from the sky. But the big stuff, like the 10-kilometer asteroids, those, we really don't want that. Those are the big asteroids that killed the dinosaurs, and it would just be a really bad day. So I have this video here that I absolutely love. We don't need sound for it because I can talk through it. And it is basically, I believe it's like a 50-kilometer asteroid, which would be a really bad day for us.
Really?
Yeah. So this asteroid is coming in towards Earth, and it heats up as it comes into our atmosphere. So it takes a little bit for it to come in. This video basically shows what would happen if this asteroid hit us. And basically it would be really terrifying because it would create this large shadow over the planet first, and so it would just get dark. Yeah, it would be a really bad day, but really bad. So you can see even in comparison, this is a pretty big,
This has gotta be slow motion,
yeah.
because.
Yeah, this would happen very rapidly. Here it's first entering the atmosphere, you can see the burning up and it smacks right into the ground. Basically then it vaporizes the atmosphere, it vaporizes a large area of debris. Yeah, so here this is vaporizing atmosphere and just the ocean in that area is gone. The rock in that area is, as you can see, flying up higher than the atmosphere. This cloud around at the bottom is actually the oceans vaporizing along with like the atmosphere just being obliterated. So that's not even just like dust. The dust is what's flying up. So actually what's flying, that big cone of debris that's flying up, is what I study for my research. I basically put in these input parameters and see what happens. So it's basically like peeling off the crust. So anything on the crust is just kind of
Oh my
gone.
goodness.
So then once all this dust and ejecta comes up, it all just falls back down. And it basically makes hell on Earth, literally. The good news is that like it would get so hot so fast that we would die almost instantly, which would be great. Because I don't want to live during this.
Jenny, you were supposed to give a nice lecture, not frighten the students. Come on. Gosh. Oh, this is what we want. Uh-oh.
So here we have mountains, and basically all of the ice is just like immediately, it doesn't even melt, it just turns to gas immediately. It just gets vaporized. So yeah.
There's North America getting greased.
Yup. Bye, North America.
Panama, bye-bye.
The Everglades, you know, just totally wiped out. Forest fires everywhere. So, yeah, this is what I define as a bad day. Like grad school's hard, but no, this is a bad day. So basically, there goes life. Nothing would survive. Yeah, so with the 10-kilometer asteroid that hit, there was actually some life that was able to survive under the water. And so like deep in vents and such, because with that impact, it didn't totally obliterate the surface of the Earth like this one would. Yes, the Chicxulub impact. That one, most of what killed life was actually the dust and debris and gases that went into the atmosphere. And so the entire crust was not ripped off. Because we still have records from before the dinosaurs, which means it couldn't have completely been torn apart. So this is the 50-kilometer impact. The 10-kilometer impact is a little bit better, and we can still regenerate life afterwards. Well, we wouldn't be able to because we'd be dead, but life in general would. And that big spot right there is where the impact happened. So it's got a big, big boo-boo. Switch back.
A big boo-boo.
So the good news is NASA is keeping track of us and looking out for us. Thanks, NASA. And they keep a catalog of all known asteroids, and they calculate the possible future trajectories. So this is one thing that I do sometimes just for fun, is just kind of like put in parameters for an asteroid and what its current trajectory is. And I can simulate where the asteroid will be in, say, 100 years, and where the Earth will be in 100 years. And if they coincide, then it's a bad day, and we need to do something about it or start planning for it. If they don't coincide, well, that's great. Yay, it's not a bad day for us. So one of the problems is that we can only see certain sized asteroids. We know that there are a lot of asteroids, but anything smaller than about 100 meters is near impossible to find with our current technology. There are some private industries that are coming up with ways to see 10-meter objects, which is really impressive. But you also have to know where to look when finding these. And so you kind of have to know exactly where it is before you actually find it. So that's fun. But we don't really need to worry about the objects smaller than 100 meters, because a lot of those will burn up in the atmosphere. Question? The trajectories, the question is, how do you know that the trajectories won't just change over time? And this goes back to Newton's principles, where an object in motion will remain in motion until another force is acted on it. And so if there's not something else that hits it or bumps it in a certain way, then it's not going to change its path very much. It might deviate a little bit due to radiation forces or some other forces, but based on just gravity, it will follow the same path. And we have tools that can simulate, do all those gravitational calculations between each body and simulate where the trajectory will come out. Any other questions? All right, well, I have a question for you guys. So if you can get out your clickers again, this is going to be a multiple choice. So if an asteroid was coming towards Earth, what would be the best way to save the planet? I mean, obviously, if we see a 50-kilometer asteroid coming towards us, we don't want to have a bad day. So we want to do something about it.
"50 kilometers, that's like from here over to Melbourne,
Mm-hmm.
roughly. It's a big piece of rock.
Yeah.
So a small chunk of Florida is coming towards Earth. What do you do? First you call Jenny Larson. Then you call Bruce Willis.
Yeah.
Okay.
Yeah, I'll give a couple more seconds here. Put in your answer. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Close. So the actual answer is to nudge it off course. I'm glad
Can you show
that. Sure, you can show that. So for some reason, 3 of you thought that it was a good idea to move everyone to the other side of the planet, hope for the best. After that video, you know, it might not be a good idea. But I'm glad a lot of you chose to move it off course. That's good. As for blowing it up, so one of the blowing up the asteroid seems like a good option at first. Like, yeah, let's just eliminate it completely. And it's a very easy solution because it's very easy for us to hit things. We're very good at aiming things and just blowing it up. But the problem is the debris from that, when it breaks apart, all the debris will still come heading towards Earth. So now instead of being hit by one big impact, we're going to be hit by millions of smaller impacts. Now a lot of it will probably burn up in the atmosphere because it'll be smaller, but it's still not good to have a large quantity of rocks burning up in the atmosphere and falling towards Earth, because we just try to avoid a lot of things hitting Earth. So the better option is to sort of push the asteroid away. So this would avoid any sort of impact at all, which is great. That's what we want to try and aim for. But the problem is it's really, really hard to do, because how do you actually push an asteroid out of the way? And that's the big issue. And we're also not very good at finding that perfect spot to push it. So to deflect an asteroid, we actually have a system where we deploy a small nuclear bomb and explode it right next to the asteroid. Not on the asteroid, but next to it. And this force from the explosion will actually push the asteroid just a little bit off course. And that little nudge will actually nudge it just enough that it'll miss Earth. So if we get too close, say we impact here, we risk breaking the asteroid. And so one of the games that I play with my research is how close is too close, and if the asteroid did happen to break during this explosion, what would the debris do? And so sometimes it's okay to get some debris, but as long as the debris is not heading towards us. So as long as the debris goes everywhere else, we're golden. And too far away, if we deploy too far away, it's not actually going to really nudge the asteroid at all. So then we're just wasting a bunch of money sending nuclear weapons out into space and blowing up nothing. But there's this nice little Goldilocks point. This isn't exact, but there's a spot near the asteroid where it's just perfect enough that any explosion and debris from the kind of blowing up next to the asteroid, that will have trajectories that either fall back on the asteroid or will fly out of the way. And it's okay if a little bit of that debris comes back towards Earth, because a lot of that will burn up in the atmosphere. And it won't be like the millions of particles flying in towards Earth, which is not a good day either. So we try and find this Goldilocks spot here. And like I said, it only really needs just this tiny nudge to push it off course. So a small bump early on in its orbit will have big changes later in its orbit. And the good news is there are only 4 asteroids right now that are on watch. And so these have the possibility of intercepting with Earth over the next 100 years. And if, like JPL, the Jet Propulsion Lab out in California, actually monitors this, and they keep an updated list online that basically shows what asteroids we see that could be hazardous. And there's someone who sits there on their computer all day looking at all the different possible asteroids that could hit us and calculating trajectories to see if it would come close to us or impact us. and making sure that we can keep track of these so that if we did have to deploy nuclear weapons to nudge it off course, that we could do so early enough that it wouldn't cause a problem, or that we wouldn't miss it, or if we did miss it and didn't nudge it enough, we could come up with a separate solution, like moving everyone to the other side of the planet, hoping for the best. Questions? Yeah?
For obviously that whole endeavor, it's like a lot of money. Does the U.S. kind of like take responsibility for that, or do they bring like a GoFundMe to the UN and say help us out? How does that work?
So for funding, questions about funding this endeavor, basically the U.S. has their own group that does this. There's a small part of the budget that goes towards NASA, a very small part, that goes towards kind of asteroid deflection and monitoring this. There are other groups, I believe, around the world who also monitor this. There isn't really a global collaboration right now anyway. There should be, since it is a global impact, literally. But, yeah. Yep.
So if an asteroid that size hit the moon, what would happen?
Question is, if an asteroid that size hit the moon, what would happen? It would also be a bad day for us, but for other reasons. So basically what would happen is what you saw happening to Earth would happen to the moon. And the problem is that a lot of that debris that flew up in the air would then be attracted towards the Earth and would fly off and hit the Earth. And oftentimes what happens, because there have been large impacts that hit moons like this, and the moon will actually be completely obliterated in a lot of cases. And it'll form just a debris disk around the central planet. And so we get it would be like having rings, except we would also probably not be alive because a lot of debris would fall on us in the process. So we wouldn't get to see the rings, but the rings would be there, and then that debris would either fly off into space, it would either form a new moon, or it would impact back on Earth and cause another very bad day for us. Anyone else? Yes?
Experiments to like test if sending out a bomb, like sending out not a nuclear bomb maybe, but like any bomb, and like if they tried to do that with an actual asteroid and see how much it would affect its course, to see how much power they would get.
So the question is about, have there been any tests done previously to see like what the power would be needed to deflect an asteroid, or how much we could deflect it? And I believe once there was a test on that. There is a mission coming up that I'm doing modeling for where basically they're not deflecting next to it, they're just ramming a satellite into an asteroid because they felt like doing that. And basically that is it's part of a planetary defense study to see what the debris would do, because this is a binary asteroid, so there are two asteroids that are orbiting each other, and one's a bigger asteroid and one's a smaller asteroid. So this actually kind of goes back to your question too, and they're actually going to be impacting the smaller asteroid, so it would be sort of similar to impacting a moon. And so what they're trying to do is just see where the debris goes. And so they're trying to see if we did actually hit an asteroid coming towards us, what would the debris look like and what would it do? And how would it impact our lives on the central body? So there haven't been a super lot of tests looking at deploying next to asteroids. This is still fairly theoretical. Thankfully, we haven't had to put it into practice too much. So, be glad for that. Yeah?
So say if something like that big hit Mercury, would we lose Mercury? It's so small.
Sorry, what was it?
If an asteroid that big hit Mercury, would we lose Mercury?
Oh, if an asteroid hit Mercury, would we lose Mercury? I don't know if we would completely lose Mercury. That's a good question. I think there's the possibility of Mercury forming a moon in that situation, which would be interesting. I kind of think that it might just kind of peel off the top layer of Mercury, and then any leftover debris would form a moon or satellite or fall into the sun. Sorry if that didn't really answer your question. Anything else?
Okay, well, Jenny will
Awesome.
be up here if you want to talk to her after we dismiss. Give her a hand, please. Very good. I'll see you next week. Click the red.
How big is Mercury?
It's, I think it's a little bit bigger than our moon. And if I was to, I didn't want to say anything while Jenny was talking.